November 28, 1943, dawn broke cold over the Sangro River in central Italy, where Royal Engineers stood knee-deep in freezing water, wrestling steel panels that weighed as much as 2 grown men. German artillery observers watched from the hills above, calling in coordinates. The engineers had maybe 3 hours before full daylight exposed them completely. 3 hours to bridge a river that had stopped armies for centuries. Every man there knew the mathematics of their situation. The Gustav Line stretched 140 miles across Italy, coast to coast, anchored by rivers like the Sangro. The Germans had blown 19 spans of the original masonry bridge, leaving only the stone piers standing like broken teeth in the current. Standard military doctrine said rebuilding would take weeks, maybe months. Field Marshal Montgomery had given them days. But the engineers weren't building a traditional bridge. They were assembling something that shouldn't work, designed by a civil servant who'd sketched the concept on the back of an envelope 3 years earlier. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today, while riding home from yet another failed bridge test. The panels they were pinning together looked too simple, too modular, too much like a child's construction toy to support 40-ton Churchill tanks. The Germans thought so too. They'd destroyed bridges across Italy, assuming the Allies would need weeks to respond. They were about to discover they'd miscalculated badly, because what those engineers were building at the Sangro that morning wasn't just a bridge. It was the solution to a problem that had plagued armies since Julius Caesar crossed the Rhine. How do you move an entire mechanized force across a river in hours instead of weeks, using equipment any soldier can carry and assemble without cranes or specialized training? The answer hung in pieces on those riverbanks. 10-foot panels, steel pins, wooden decking, components so standardized that parts made in Manchester could and connect perfectly with parts made in Detroit. The Bailey Bridge looked absurdly simple, which was exactly the point, because in military engineering, simplicity wasn't just elegant, it was survival. The problem started decades before the first shot of World War II. In 1917, British tanks at Cambrai weighed 18 tons. By 1939, the Matilda tank weighed 23 tons. The Churchill, rolling off production lines in 1941, weighed 40 tons. Infantry divisions needed bridges that could move these monsters across rivers while under fire. The British Army's standard portable bridge, the Inglis, dated from World War I. It could handle 19 tons, maximum. Do the math. A 23-ton tank plus ammunition, fuel, and crew modifications pushed the total weight to 26 tons. The Inglis failed before the tank reached mid-span. Engineers needed something stronger, but everything stronger wasn't portable. Traditional bridges solved this problem with complexity. Steel girders custom-fitted to specific spans, concrete foundations poured to exact specifications, support structures that required weeks to construct, and cranes that weighed more than the bridges themselves. This worked fine in peacetime. In war, it meant watching your offensive die at the river's edge while defenders regrouped. The French learned this in May 1940. When German panzers reached the Meuse River, they brought prefabricated pontoon bridges that assembled in 8 hours. The French were still waiting for traditional bridging equipment to arrive. German forces crossed 60 divisions in 3 days. France fell in 6 weeks. The speed advantage at river crossings didn't just influence the battle. It decided the war. The mathematics were brutally simple. A single armoured division needed to move 15,000 men, 3,000 vehicles, and hundreds of tons of supplies across a river in under 12 hours to maintain offensive momentum. Any longer, and defenders could establish new positions, bring up reserves, dig in. Rivers weren't just obstacles, they were reset buttons that gave losing armies time to recover. And Europe was full of rivers, the Rhine, the Seine, the Loire, the Po. Intelligence estimates suggested the Wehrmacht had pre-wired over 2,000 bridges between the Atlantic coast and Berlin for demolition. Every major river crossing would become a choke point where hours mattered more than firepower. The side that could bridge faster would control the pace of the entire war. British engineers understood this. They'd been testing portable bridge designs since 1938, watching prototype after prototype fail. Too heavy to transport, too weak to carry tanks, too complex to assemble under fire, too specialized, requiring parts that couldn't be manufactured quickly enough. The engineering specifications read like contradictions. The bridge needed to be strong enough to support 40-ton tanks, light enough that 6 men could carry each component, simple enough that soldiers with minimal training could assemble it in darkness, modular enough to span anything from 30 feet to 300 feet, and manufacturable at scales that could replace thousands of demolished bridges across multiple theatres simultaneously. Every major shipyard and engineering firm in Britain looked at those requirements and said the same thing. Impossible. You couldn't have strength and portability. You couldn't have simplicity and adaptability. Pick 2, maybe 3 if you got lucky. But all of them? The physics didn't work, which is why the solution came from someone who wasn't trying to build a better traditional bridge. He was trying to rethink what a bridge fundamentally was. Donald Coleman Bailey was born in Rotherham, Yorkshire, in 1901. He graduated from the University of Sheffield in 1923 with an engineering degree and spent the 1930s designing railway bridges. Nothing glamorous. Nothing that suggested he'd invent one of the 3 most important technologies of World War II, according to Eisenhower himself. By 1940, Bailey worked as a civil servant at the Military Engineering Experimental Establishment in Christchurch, southern England. Not a decorated officer, not a flashy innovator, a methodical designer who spent his days testing other people's bridge prototypes and watching them fail. The insight that changed warfare came on an ordinary afternoon in late 1940. Bailey had just witnessed another bridge test fail spectacularly. The prototype couldn't handle the weight. The assembly process required specialized tools that soldiers couldn't operate under pressure. The components were custom-fitted, meaning if you lost one critical piece, the entire bridge became useless. Bailey rode back to headquarters in silence, thinking about everything he'd just watched go wrong, and somewhere between the test site and his office, he understood something that had escaped every other military engineer. The problem wasn't making bridges stronger, it was making them simpler. He pulled an envelope from his pocket and started sketching. Rectangular panels, 10 feet long, 5 feet high. Standardized connections at 4 corners. No custom fittings, no specialized tools, no unique components. Just identical panels that connected with simple pins. Stack them vertically for strength. Connect them laterally for width. Pin them together end to end for length. Like building with Meccano, the children's construction toy. Except this Meccano set would change military history. The concept violated every principle of traditional bridge engineering. Conventional wisdom said bridges needed custom designs for specific spans. Bailey's panels were identical, regardless of span length. Traditional engineering used specialized components for different load requirements. Bailey used the same panels, just adding more of them for heavier loads. Established bridge builders argued this approach wasted material. Why use standardized components when custom fittings could save steel? Bailey's answer was cold logistics. Custom components meant custom manufacturing, which meant slower production, which meant you couldn't build thousands of bridges simultaneously. Standardization meant any engineering firm with basic steelworking equipment could manufacture panels. More manufacturers meant exponentially faster production. The panel design itself was elegant in its simplicity. Each panel was a welded steel truss, 10 feet long by 5 feet high, with crossbeams at each end and center. 8 interior beams reinforced the corners, creating geometric diamonds within the rectangular frame. The entire panel weighed 600 pounds, heavy enough to be strong, light enough that 6 men could carry it using simple lifting bars, 4 holes at the corners aligned with adjacent panels. Pins hammered through the holes locked panels together. Cross bolts through the pins prevented them from working loose. No welding required in the field. No cutting, no fitting, no modifications. If a panel was damaged, you simply replaced it with another identical panel from stock. The floor system used transoms, basically floor beams, at 6-foot intervals. Steel stringers connected the transoms. Wooden planking laid across the stringers created the roadway. Later in the war, steel plates replaced the wood for better protection against tank tracks, but the core principle remained. Simple, standardized, replaceable. The real innovation was the launching method. Traditional bridges required building the entire structure in place, which meant engineers working directly over the gap they were trying to span. Bailey's system built the bridge on shore, then pushed it out across the gap on rollers. One 10-foot section at a time, building from the home bank toward the far side. Engineers assembled the first section completely: panels, transoms, stringers, decking. When that section was ready, they pushed it forward on rollers until it nearly reached the point of balance. Then they built the next section and pushed the entire bridge forward again. A temporary nose, a lightweight guide structure, extended ahead of the actual bridge to provide support as it crossed the gap. When the nose reached the far bank, it supported the bridge while engineers completed the final panels. Then they removed the nose and rollers, locked the bridge to abutments on both banks, and it was ready for traffic. The entire process could happen without engineers needing to work over the river itself until the final securing phase. This meant they could build under artillery fire with significantly reduced exposure. Traditional bridge construction required engineers standing in the open directly over water, perfect targets for enemy artillery observers. Bailey's method kept most construction activity on the home bank, behind whatever cover existed there. The War Office received Bailey's formal proposal in February 1941. The timing was desperate. France had fallen. The British Expeditionary Force had evacuated from Dunkirk. Operation Barbarossa would begin in June. Everyone knew Allied forces would eventually invade occupied Europe, and every strategic planner understood river crossings would determine success or failure. Bailey's proposal arrived with detailed drawings, stress calculations, and material specifications. The War Office scheduled full-scale trials for May 1941 at Christchurch, giving Bailey and his team just 3 months to build a working prototype. They constructed the test bridge over Mother Silla's Channel, a waterway cutting through Stanpit marshes near the experimental establishment. The bridge still stands there today, nearly 80 years later, a functioning reminder of where modern military bridging began. For the initial tests, Bailey's team built a simple span, single panels stacked once vertically, once horizontally, just enough to prove the concept worked. The stress testing followed standard procedure, but with limited equipment. Load the bridge until it fails, then calculate safety margins. Bailey needed to prove his design could handle 40 tons, the weight of a Churchill tank, but wartime rationing meant he couldn't access multiple Churchill tanks for testing, so he improvised. Engineers drove a World War I Mark V tank onto the test bridge and parked it at midspan. The Mark V weighed 28 tons. Not enough to prove the 40-ton requirement, but enough for preliminary testing. Bailey instructed workers to remove the support jacks beneath the bridge. If the panels held the 28-ton Mark V without support, the design had promise. The bridge held. Steel panels creaked under load but didn't deform. Pin connections remained tight. The structure distributed weight exactly as Bailey's calculations predicted. Engineers then built a platform on top of the Mark V and loaded it with smaller contemporary tanks, adding weight incrementally. The bridge still held. The War Office observers weren't convinced yet. One test over a narrow channel wasn't proof of battlefield viability. They demanded longer spans, heavier loads, faster assembly times. Over the following months, Bailey's team conducted dozens of tests, each more demanding than the last. They built longer bridges, stacking panels 2 and 3 high to create multi-story trusses. They loaded test bridges with the heaviest equipment available, including fully loaded lorries and artillery pieces. Every test produced the same result. The design worked. More importantly, it worked better than traditional bridge designs. A standard English bridge required 12 to 15 men to maneuver each heavy box girder section. Bailey panels needed 6 men. Inglis bridges required specialized lifting equipment. Bailey bridges needed only sledgehammers, wrenches, and rollers. Assembly speed improved with each test. The first complete bridge took engineers 16 hours to construct, working carefully and methodically. By the 10th test, trained crews completed the same span in 8 hours. After 20 tests, assembly time dropped to 6 hours. Not perfect yet, but already faster than anything else available. The modularity proved more versatile than anyone anticipated. Need a longer span? Add more panels? Need more load capacity? Stack panels vertically, or add additional panels horizontally, crossing a partially destroyed masonry bridge with stone piers still standing? Build the Bailey span between existing piers instead of spanning the entire river. That last capability turned out to be crucial in Italy, where retreating German forces demolished steel bridge spans but often left stone piers intact. The British didn't need to span 300-foot rivers. They needed to span 40 or 50 feet between surviving piers. Bailey bridges did that perfectly. By July 1941, the War Office authorized full production. Over 600 British firms received contracts to manufacture components. Littlewoods, better known for mail-order catalogues, converted factory space to produce panels. Small engineering shops that normally made agricultural equipment started fabricating transoms and pins. Production rose to 25,000 panels monthly by 1943. The standardization Bailey insisted upon made this distributed manufacturing possible. Every firm worked from identical specifications. Panels manufactured in Birmingham connected perfectly with panels made in Liverpool. Tolerances were tight enough that no field modifications were ever needed. You could mix components from a dozen different manufacturers and build a bridge without worrying about compatibility. The Americans recognized the design's value immediately. In early 1942, the United States Army Corps of Engineers licensed the Bailey design and began domestic production. They called it the Portable Panel Bridge initially, though most American soldiers just called them Bailey bridges like everyone else. American manufacturers produced panels with slightly different steel alloys than British specifications, but maintained identical dimensions. British and American components were completely interchangeable. This transatlantic standardization paid unexpected dividends later in the war. When Allied forces fought together in Italy and later in France, British and American engineering units could pool their Bailey equipment freely. Run short of panels building one bridge? Borrow American stock. Need extra transoms? British supplies worked perfectly. No compatibility issues. No modifications required. The first operational Bailey bridge saw combat in November 1942 in Tunisia. The 237th Field Company, Royal Engineers, built it over the Medjerda River near Medjez el Bab on the night of November 26th. German forces held high ground overlooking the river. Engineers worked in darkness, assembling panels by feel, pushing the bridge across the river section by section. Artillery fire bracketed them twice during construction. They kept working. The bridge opened at dawn. Tanks crossed immediately, armor that would have been delayed days or weeks using traditional bridging methods. The Germans counterattacked within hours, trying to destroy the bridge with artillery. They failed. Even when shells damaged panels, engineers simply removed them and pinned in replacement panels from stock. The bridge stayed operational. That single crossing established the pattern that would repeat thousands of times over the next 3 years. Engineers building Bailey bridges under fire, sections damaged by artillery, rapid repairs using identical replacement parts, armor crossing within hours of river obstacles being encountered. The tactical implications were profound. River obstacles that should have stopped offensive operations for days became minor delays. This fundamentally changed how commanders planned campaigns. Before Bailey bridges, you planned invasions around existing bridge sites or spent weeks preparing river crossings. After Bailey bridges, you attacked where enemy defenses were weakest and bridged rivers as needed. The bridge adapted to tactics instead of tactics adapting to available bridges. The Italian campaign showcased this flexibility spectacularly. Allied forces landed in Sicily in July 1943 and fought their way up the peninsula for the next 22 months. German forces implemented a deliberate retreat strategy. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this, blowing every bridge as they withdrew. They weren't just denying river crossings, they were buying time for defensive positions farther north. In Sicily and mainland Italy combined, the US Fifth Army and British Eighth Army constructed over 3,000 Bailey bridges. End to end, those bridges stretched 55 miles. Average bridge length was 100 feet, though individual bridges ranged from simple 30-foot spans over minor streams to engineering marvels like the Sangro River crossing. The Sangro Bridge became legendary among engineer units. The German demolition team destroyed 19 of the original masonry bridge's steel spans, leaving 11 stone piers scattered across 343 meters of river. British engineers looked at those piers and saw opportunities instead of obstacles. They didn't need to span the entire river. They needed 11 separate Bailey bridges, each spanning the gaps between existing piers. Construction began on November 24, 1943. Engineers worked under constant German observation from hills overlooking the river. Artillery fire was continuous, but not overwhelming. The Germans couldn't mass enough guns to completely suppress construction without exposing their artillery positions to Allied counter-battery fire. So both sides endured a grinding exchange. German observers called in coordinates. Allied engineers kept building. The modular system proved its worth immediately. Engineers didn't build one massive bridge. They built 11 smaller bridges simultaneously, using different engineering teams for each span. Some spans required only single-story panels. Others needed double or triple-story construction to handle heavier loads. The flexibility meant optimizing each span for its specific requirements without needing custom components. 9 days after construction began, the Sangro Bailey Bridge opened to traffic. At 1,126 feet end-to-end, it was the longest Bailey Bridge built to that point. Field Marshal Montgomery personally attended the opening ceremony, bringing photographers and journalists. The symbolism mattered. The Germans had demolished a major river crossing, expecting weeks of delay. The British rebuilt it in days. Traffic flow across the Sangro illustrated why Bailey bridges changed warfare. Within 72 hours of opening, over 2,000 vehicles crossed. Tanks, artillery, supply lorries, ambulances, reconnaissance units. Everything an army needs moved across that river at operational tempo. The German defensive line anchored on the Sangro collapsed within a week because defenders couldn't maintain their positions with Allied armour operating freely north of the river. Compare that to earlier Italian operations where blown bridges stalled Allied advances for weeks. The Trigno River crossing in October 1943 took 36 hours to bridge using conventional methods. One bridge, 36 hours. The Sangro crossing built 11 bridges in 9 days using Bailey equipment. The time advantage alone justified every pound spent developing the system. But speed wasn't the only advantage. Bailey bridges stayed operational under conditions that destroyed traditional bridges. At the Rapido River, in January 1944, German artillery scored direct hits on a Bailey bridge during initial assault crossings. 3 panels were destroyed. Engineers replaced them with spare panels in under 2 hours. The bridge reopened before most soldiers realized it had closed. Try that with a conventional steel truss bridge. Direct artillery hit typically meant complete reconstruction. The damaged section couldn't be repaired in place. You needed to build a new bridge elsewhere, or accept the river as impassable. Bailey's modular design turned catastrophic damage into minor inconvenience. Destroyed panels got replaced like spare tires on a lorry. The psychological impact on German defenders was significant. They'd spent 2 years learning that demolished bridges bought them time. Days, sometimes weeks of breathing room to establish new defensive lines. Bailey bridges collapsed that assumption. Blow a bridge at dawn, and watch Allied engineers assembling a replacement by noon. Watch armour crossing by sunset. The demolition effort that cost German engineers hours of careful explosive placement brought maybe 12 hours of delay. German forces tried adapting. They started demolishing not just bridge spans but also the approaches, making it harder for Bailey bridges to reach the river. They mined approach roads, cratered them with heavy explosives, destroyed buildings that might provide cover for engineering operations. It helped, but only marginally. Bailey bridges still went up faster than anything Germans could destroy. The Wehrmacht had their own portable bridge systems. The Kriegsbrücke B and later designs could handle tank loads across moderate spans. But German bridges required more specialized equipment, longer assembly times, and couldn't be manufactured at Bailey production scales. By 1944, German engineer casualties and equipment losses meant portable bridge equipment was perpetually in short supply. Allied forces could afford to lose Bailey panels to enemy fire because production exceeded consumption. Germans couldn't. This material advantage compounded tactical advantages. Allied commanders knew they could force river crossings aggressively because their engineers could bridge under fire. German commanders increasingly ordered retreats before Allied forces reached river lines because they knew bridges wouldn't stop the advance long enough to matter. The Bailey Bridge didn't just speed up Allied operations, it degraded German defensive planning. The bridge's impact extended beyond tactical river crossings. Engineers adapted Bailey components for uses Donald Bailey never imagined. The basic panel became a universal construction element. Need an elevated roadway over boggy ground, build a Bailey panel structure and lay decking on top. Need a temporary dock for landing craft? Bailey panels provided the framework. Need a radio tower? Stack panels vertically, and you had a 40-foot tower in a few hours. British forces in Burma built a Bailey suspension bridge over the Volturno River at Triflisco. Standard Bailey panels formed the deck, but engineers added cable suspension systems for longer spans. That bridge carried 240,000 vehicles over 8 months, demonstrating the design's durability under sustained heavy traffic, a temporary expedient lasting months under wartime conditions. The Rhine crossings in early 1945 represented Bailey bridging's finest hour. The Ludendorff Bridge at Remagen, captured intact in March, couldn't handle all traffic Allied forces needed to push into Germany. Engineers supplemented it with Bailey pontoon bridges, mixing standard panels with floating pontoon supports. Within days, multiple Bailey bridges crossed the Rhine at various points, none dependent on the Remagen Bridge's increasingly precarious structural condition. The longest Rhine crossing, called Blackfriars Bridge, stretched 558 metres. Royal Canadian engineers of the 2nd Canadian Corps built it near the Dutch border, working through heavy fog that delayed component delivery. The floating section alone rated military load class 40, meaning 40-ton tanks could cross safely. Construction took 2 days despite weather delays. 2 days to bridge the Rhine. Napoleon would have killed for that capability. Total wartime production exceeded 700,000 panels, enough to stretch from London to Leningrad, 2,000 miles of potential bridging. Over 4,500 bridges were built during the war, at an average length of 100 feet. Some stayed operational for weeks. Others were destroyed by enemy fire and rebuilt the next day. The system absorbed losses and kept functioning. The human cost of building these bridges rarely appears in official histories. Engineer units worked exposed, often under direct enemy observation. Artillery observers specifically targeted bridge construction sites because stopping a bridge stopped an entire army's advance. Engineers couldn't dig foxholes in the middle of rivers. They couldn't take cover when shells fell. They had to stand in the open, holding panels overhead, pounding pins while mortar rounds walked toward them. Casualty rates for combat engineer units consistently exceeded infantry rates during river crossing operations. A study of British engineering losses in Italy showed that engineers suffered 30% higher casualties than infantry during assault operations. They were in the most dangerous positions, doing the most critical work, with the least protection. Yet assembly times kept improving. Experienced Bailey Bridge crews could build a simple 60-foot span in 3 hours, under ideal conditions. Under fire at night in rain, the same bridge might take 6 hours. but 6 hours still beat 2 weeks. The efficiency came from rehearsal. Engineering units practiced Bailey assembly obsessively. Crews assembled and disassembled bridges, until every step was automatic. Soldiers learned to work by touch in darkness, knowing exactly where each pin went, which panel connected where. The U.S. Army established training facilities where engineering units practiced on mock rivers, simulating combat conditions. Live fire exercises included artillery simulators and smoke generators. Units practiced building bridges under simulated enemy fire until they could maintain construction tempo, despite explosions and chaos. This training paid off. American engineering units often matched or exceeded British assembly times despite coming to Bailey equipment later in the war. The end of European combat in May 1945 didn't end Bailey bridge usage. Post-war Europe's infrastructure was devastated. Thousands of bridges remained destroyed. Bailey bridges became the temporary solution that became semi-permanent. Many stayed operational for years while permanent replacements were constructed. Some stayed so long they were upgraded with steel decking and reinforced panels, essentially becoming permanent fixtures. The Australian Army donated surplus Bailey equipment to Papua New Guinea in the 1960s, where some bridges remained in daily civilian use until the 1990s. Half a century of service for bridges designed as temporary military expedients. That durability came from over-engineering. Bailey, designed for worst-case military loads. Civilian traffic, even heavy lorries, was relatively gentle by comparison. Modern military forces still use Bailey-derived designs. The British medium girder bridge, introduced in 1971, used aluminum panels instead of steel, reducing weight from 600 pounds to 300 pounds per panel, but the core principle remained identical. Standardized modular components assembled without specialized tools. The MGM served British forces for decades before being replaced by more recent designs that still trace their lineage to Bailey's original concept. The United States Army's current improved ribbon bridge uses floating bay sections that deploy hydraulically in minutes. But examine the connection systems, and you find pin and bolt assemblies conceptually identical to Bailey's design. The launching method, building on shore and pushing across water on rollers, is pure Bailey doctrine. Modern materials and manufacturing allow faster deployment, but the engineering principles are unchanged. NATO standardization agreements established in the 1970s mandate that member nations' military bridging equipment must be intercompatible. British, German, American, and French bridge components can connect to each other. This requirement comes directly from World War II experience, where hybrid bridges combining Allied equipment worked successfully because Bailey standardization made it possible. The lesson stuck. Interoperability matters more than national pride in bridge design. Civilian disaster relief organizations maintain Bailey-type bridge stockpiles, specifically for emergency deployment. When the 2010 Haiti earthquake destroyed Port-au-Prince's road network, international relief teams airlifted Bailey components and had 3 major crossings operational within 72 hours. The same principle that worked under German artillery fire worked in earthquake devastation. Simple, standardized, rapidly deployable. The 2011 Tohoku earthquake in Japan saw military engineers deploy modular bridges based on Bailey principles to restore coastal access roads. The 2004 Indian Ocean tsunami, Hurricane Katrina, the Pakistan earthquake. Every major disaster sees Bailey-derived bridges appearing within days because nothing else can be deployed that quickly at that scale. Donald Bailey was knighted in 1946 for his contribution to Allied victory. He received £12,000 from the Royal Commission on Awards to Inventors, equivalent to about £500,000 today. Modest compensation for designing one of the 3 most important technologies of the war, but Bailey wasn't motivated by money. He was an engineer solving a problem, and the problem was solved. He died in May 1985 in Bournemouth, largely unknown outside engineering circles. Despite his bridge being used on every continent and saving countless lives, most people have never heard his name. There's no Bailey Memorial on the National Mall, no aircraft carrier named in his honour, just a small section of bridge preserved in Christchurch, where it all began, and thousands of bridges worldwide still built on his principles. Field Marshal Montgomery's assessment was blunt and accurate. He couldn't have maintained the speed and tempo of Allied advances without large supplies of Bailey bridging. General Eisenhower placed it in his top 3 technological developments of the war, alongside radar and heavy bombers. The bridge that looked like a child's toy, too simple to work, turned out to be the solution nobody expected. The legacy isn't just military, it's conceptual. Bailey proved that simplicity could triumph over complexity when properly applied. That standardization, often derided as crude or wasteful, enabled capabilities that custom engineering couldn't match. That design elegance came not from sophistication but from ruthlessly eliminating everything unnecessary. Wars are still fought across rivers, bridges are still built under fire, and when engineers need to cross a river in hours instead of weeks, they still reach for modular panels and simple pin connections. The specific materials have changed, the methods are faster, but the fundamental principle Donald Bailey sketched on an envelope in late 1940 remains the foundation of rapid military bridging. He took the oldest obstacle in warfare, rivers that stopped armies cold, and turned them into minor inconveniences. That envelope sketch changed not just World War II, but warfare itself. The Germans blew thousands of bridges trying to slow Allied advances. The Allies rebuilt them faster than the Germans could destroy them, and in that race between demolition and construction, Bailey's simple design proved more powerful than any amount of explosives. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.